one lecture.
Hi, everybody. Thank you for having me. So I'm going to continue in Rick's talk about high-dimensional expanders. By the way, do you hear me? Is this on? Good. So I'm going to continue with Irit's talk about high-dimensional expanders and all the spectral treatment of these objects. And in this hour, we're going to focus on a theorem that's by Isar Oppenheim, who's also sitting here, which we like to call the trickling down theorem. And I'll state the theorem again in a second, even though Irit stated it in the last hour. The reason why we're dedicating a full hour to this theorem is because it demonstrates a very nice phenomenon in simplicial complexes where we can really exploit the local structure of the links and actually get meaningful global behavior. So let me just state the theorem and then we'll discuss it a bit. So the theorem is as follows. Suppose we have a d-dimensional simplicial complex X, okay, and we should think of D to be at least 2, and it's okay to keep in our mind just the case where D is equal to, okay, so all we care about is like vertices, edges, and triangles. And suppose two things. The first thing is that for every vertex, okay, xv is very well connected. What do I mean by very well connected? It is a lambda one-sided spectral expander. And the second assumption, which is a bit more technical, is that we also suppose that the underlying graph of G of X is connected. Okay, so this is our setting. We have a d-dimensional simplicial complex. Its links are well connected, one-sided spectral expanders, and the underlying graph of X, when we consider only the vertices and the edges, is just connected. Then the underlying graph is also very well connected. What do I mean? It's not necessarily a lambda one-sided spectral expander, but it's another constant that depends on lambda, lambda over 1 minus lambda. Okay, so in essence, what does this theorem mean? Suppose that we have our simplicial complex, and for every vertex, if I look at its neighborhood, it's locally a very well-connected graph. So from, okay, then if the underlying graph itself is also connected, then it means that this like local connectiveness trickles down to the property of to be well connected also in the underlying graph itself. So this is one version of the theorem where we can take links of the vertices and infer something about the global underlying graph. A stronger version of the theorem can actually take links of higher levels, okay, and then use this theorem iterated again and again to get good expansion in all links. Okay, so what do I mean by this? Suppose, for example, now that D equals 3, okay, and now I know that for every edge E, okay, the underlying graph of in the link of E is like a lambda one-sided spectral expander. Then if I take this theorem and I look at links of vertices, okay, then if I take a vertex V and I look inside xv, okay, the links of the vertices inside XV are actually links of edges in the global graph X. Okay, so when I know good expansion happens on the level of edges, I can use this theorem to infer good expansion in the links of the vertices, and then I can use this once again to get good expansion also in the global level. So in fact, we can write a stronger version of this theorem.
Maybe you delete the previous.
Oh, yeah, I thought maybe I leave the definition above because I'm going to use it, but maybe later I'll also delete it. So our stronger version is let X be a d-dimensional simplicial complex such that for all faces of codimension 2, XS is a lambda one-sided spectral expander, and 2, the underlying graph of every link is connected then X is also a one-sided spectral high-dimensional expander. Okay.
So when you say every link, you mean every link of every face?
Every link of every face in every level.
Of codimension at least
Of
2.
codimension at least 2. Of course, the trivial links of codimension 0 or 1 can't be connected because they're either the empty set or just a bunch of vertices. And how much is this constant? Well, if you compose this function on itself again and again, it becomes this function. So so this is a bit worse than this. However, if we know how to construct simplicial complexes where on the faces of codimension 2, this lambda can get arbitrarily close to 0, then this will also get arbitrarily close to 0. So this is good. Very well. So we will see in the proof of this theorem that it uses again a very nice idea that yes.
So in this theorem, the part 1, whatever the assumption is it spectral expander as a graph or as like high dimension? This definition of high dimension.
So if I look at
I'm talking about this one. Here.
This one.
Yeah.
Yeah. So I'm just talking about spectral expanders as a graph. Okay.
It's like only the one skeleton.
Yes, I'm looking only at the one skeleton.
Oh, I see.
Yes. So
this theorem is just a theorem about graphs. There is no simplicial complexes.
So here there is a simplicial complex, but actually all we care about are up to the triangles. Because I look at these links as graphs themselves. Okay, but you're correct that actually we don't care about higher dimensional faces. Okay, in this theorem we already do care about high dimensional faces. However, this theorem is just to reapply this theorem again and again to trickle down the expansion.
So do you have two-sided versions of?
Yes, so that was one comment that I wanted to say. Is in this theorem you bound the eigenvalues of the adjacency operator of the global adjacency operator by the positive side by lambda, and there's also an analogous theorem, or actually you can state the theorem also for negative eigenvalues. So if I know that all the eigenvectors of the links are also bounded from below by some, I don't know, some eta, okay? So then we will get that the negative eigenvalues also of the global adjacency operator will also be bounded by the same bound, okay, just here from below. And in fact, And in fact, the negative side of the theorem is even meaningful when this eta is equal to -1, which is like the trivial bound for the eigenvectors of the adjacency operators from below. Okay, because they're averaging operators, lambda n is also always bounded from below by -1. And what you get from here is that the lower you go in a high-dimensional simplicial complex, the further bounded you are from below. Okay, so we didn't discuss this too much, but to be bounded from below is like to be far from being bipartite. And the negative part is supposed to sound intuitive, because if we are in a simplicial complex who has many levels, whose dimension is high, then of course you're very bounded from being bipartite, because every vertex, because it must be inside at least one d-dimensional face, then it means that the underlying graph, okay, every vertex like participates in a very large clique. So as cliques themselves are supposed to be very far from being bipartite, the negative part is supposed to correspond to this intuition. Great. So thank you for that question. I'll just say that this theorem again has like a very nice proof, and I think it's for the proof alone it's good to like dedicate a full hour. But I should say that this theorem also has applications as a tool in analyzing simplicial complexes themselves, because before this theorem was known, to show that some simplicial complex is actually a high-dimensional expander, you needed to look at the expansion in all the links. And here, if you only want a bound on the expansion of all links, you only need to consider links of codimension 2, and you only need to analyze them and to show something that's usually much weaker, just that the underlying graph of all the other links is connected. So Isha, Oppenheim, and Tali Kaufman also have a nice construction of high-dimensional expanders that uses like elementary group theoretic ideas, and there they rely on this theorem to only like analyze links of codimension 2, which have a very nice and relatively simple description. So let's maybe talk about the intuition of why this thing is supposed to be true. So first of all, why do we need this like technical assumption that the underlying graph of X is connected? Suppose that I have two copies of the complete complex. Each one is supposed to be a very good spectral expander, even two-sided. And indeed, if I look at a simplicial complex, which are just both of these copies, okay, but they're disjoint from one another, they're disconnected, sorry, then of course, all the links in each copy seem very well connected. So I have no chance to sense that this graph is disconnected, even if the links are very well connected. However, if they weren't completely disconnected, they were just, I don't know, a sparse cut in this underlying graph, then this sparse cut should have probably appeared, okay, in a link of some vertex in some side, okay? And somehow, if this cut was sparse, then you would probably imagine that even in the link, the cut should have been sparse. So then you can say, okay, so it couldn't just be, a few edges. Maybe I have to put here another few edges, and then somehow you'd imagine that if I put here more edges, then they would be visible in more links, etc., etc. However, this is just intuition, and what we will see in a moment is that the proof actually doesn't go in these lines. We actually use other ideas that relate more to the spectral definition of expansion. So the combinatorial definition of expansion of connectedness, it's not maybe so clear in this proof how it actually comes into play. Okay, so So without further ado, let's maybe prove the theorem. So last hour, recall that we defined the adjacency operator, right? So if we have a function f on the vertices of the underlying graph, then AF is also a function on the vertices, and AFV is just the expectation over all the u's adjacent to V of f of u. So if this is V, and this is its neighbors, then f is just averaging out all the neighbors of V. And we saw last time that for functions f and g on this, we can define an inner product that is the global average on all the vertices of fv times gv. And we saw that if we take AF and take its inner product with some function g, then this actually corresponds to this like symmetric bilinear form where you choose like an edge with a direction and then multiply f of one side times g of the other side. Doesn't matter which is which. Good. So the main idea in
the weights that irritate.
Yes, of course. So I'm
come into the play.
Yeah, so I'm taking here expectation, and the expectation is, of course, according to the weight in the simplicial complex. Okay, so it's not just necessarily uniformly at random chosen edge, when in fact I'm sampling it in the way that we talked about last time, where I have a measure on the triangles or on the top level faces, and then I choose according to this and remove one vertex uniformly at random until I get an edge. So one of the main...
So don't we, aren't we supposed to see it somehow, which weight you chose for the triples? The two faces? I mean, that should affect the statements, no?
The statement?
It's only behind the scene, we never see it directly out.
Oh, so now we're going to exactly see how the structure of the simplicial complex, where we have like faces that are one above, actually give us more information on this form. So in fact, one of the main ideas in this proof is that in a simplicial complex, we can actually calculate this symmetric bilinear forms by the local adjacency operators in the link. So this method where we take some global invariant or global form and calculate it using the local structure is, I think it was first due to Garland. He used it in a different setting, but the spirit is quite similar. So let me write precisely what I mean. Okay, so suppose f and g are real-valued functions on the vertices. Okay. Then, first of all, I can calculate this inner product of f and g by first choosing u, and then calculating the local inner product of f and g inside the link of u. And the second is the same thing, but with the adjacency operator. If I look at AF inner product with G, then I can calculate it by using the local adjacency operators and the local inner products in the links. So here when I say f of u and g of u, I just mean the restriction of f to all the vertices participating in the link of u. And when I write a sub u, Okay, it's just a local adjacency operator in the link of U when I think of it only as a graph. Okay, its underlying graph. So it's a very good question, and in fact, the fact that we are looking at a simplicial complex will allow us to calculate this global adjacency operator, this global inner product, as a convex combination of the local inner products inside the links. So let's see why this is true. So for the first item, F inner product with G is again just it's just an expectation over V of FV times G of V. And right in here we're like sampling V out of X0. And let's remember how we sampled V out of X0. Okay, we first sampled like an edge UV, and then out of it, right, we take one vertex uniformly at random. Okay, and what do I mean by we sampled UV? Again, we remember that there is a simplicial complex, so even to sample this edge UV, we maybe needed to sample a triangle or a foreface or whatever, and then we removed vertices uniformly at random. But as you can see, I can sample this edge in the marginal of this process where I sample many high-level faces, and then out of it I take V, and this will be the same marginal that I'm using here to just sample V. So the point is, when I do this process, I can first condition on the vertex that I'm sampling in the edge, but I'm not using, but I'm throwing away. Okay, so this is equivalent to first sample U, okay, out of X0, then sample an edge UV, but conditioned on the fact that this edge contains U, and then just take the other vertex. Okay? But this second step of sampling an edge UV given that it contains U, okay, is precisely like sampling V according to the link of U. Okay? So if we calculate this through the conditional expectation of this U, which is sampled at the other side of this edge, this is, again, just like first sampling U, and then I output FVGV precisely when I sample V out of the link of U. And this is why I can write here F sub U, G sub U, as an inner product in the link of U. Is this clear? Good. So what should I do for the second item? The answer is exactly the same. So if I look at AF inner product with G, this is, as we said before, just to sample an edge according to X1, UV, and outputting F of U, G of V. And again, this sample, right, I can look at it as sampling UVW out of the triangles, and then just removing one vertex. Okay, just taking maybe the first two and removing the third. Okay, and again, this is equivalent to first sampling W and then sampling a triangle, given that W participates in it. And again, sampling this triangle given W precisely because the way we built the measure on the links is exactly equivalent to sampling UV inside the edge set in the link of W. Okay? So what do we get here? expectation over this W of expectation UV inside the link of W, FUGV, and what we see is that inside, what we get here is precisely the local adjacency operator operating on F and then inner product with G. So, in fact, this is like, this claim that I wrote over here is like the main observation that, that Izhar had that was in the spirit of Garland's method. And this is like the main lemma inside the proof, I think. So let's prove the theorem. Okay, so what do we need to prove? Let's take, let gamma be some eigenvalue of the underlying, the global, like the underlying graph of X, okay? Let's call its adjacency operator A. Good. So, and let's take F to be an eigenfunction corresponding to this gamma. Okay, and what we saw in Irit's talk is that without loss of generality, we can request that F will be perpendicular to the all ones function. And another thing that I want to assume is that F is normalized. Okay, its norm is 1. So what do we need to show? We need to show that gamma, right, is less or equal to lambda over 1 minus lambda, assuming that, that the eigenvalues of the local adjacency operators are all less or equal to lambda. So how can I write this gamma? I can write it just as AF inner product with F. Because AF is lambda F, and then I can remove it outside of the inner product, and then I will get precisely this. And by our localization claim, this is just equal to expectation on all V, AVFV inner product with FV. And when it's clear from the context, I'm not going to write here the link of where this inner product takes place. And good. So now we like translated the question of how large this is to a question on a bunch of local operators. So here's maybe, I don't know, here's like a naive way to continue this proof. Suppose that we could have shown that if F was perpendicular to the global all ones function, it will imply that all these local functions were also perpendicular to like the local all ones function in the link. Then what could we say? We could say, okay, so this this AVF FV FV would be less or equal to lambda FV FV. And when I would take expectation over this, right, it will be equal lambda, and then we would get like that gamma is less or equal to lambda. So if I could wish that all these were perpendicular to the local all ones function, it would be great. Then I would prove the theorem, and then I would be happy. However, this is not only something that we don't know how to prove. It is in fact untrue, and like any counterexample will show it, right? Even on, I don't know, the complete complex, what does it mean to be perpendicular to the global constant? It's just to mean that your weighted average is 0. So if we're on the complete complex, I don't know, maybe half the vertices say 1 and half say -1, and then we would be then we would be perpendicular. However, if I look at a link in the complete complex, right, it's like all the vertices except one. And in this link, right, even if I was globally perpendicular, locally I have no idea. I can maybe even be in some functions like largely positive and then some largely negative. All I know is that the average is supposed to be 0. So this doesn't hold. So we have no other option than to just consider it in our calculations. So let's decompose every local function, okay, to like what we called f0 plus f_perp, okay, where f0, fv0, and fv_perp, because we're doing it locally, and fv0 is just some constant times the local all ones vector, and fv_perp is just the component that's perpendicular to it. And now let's deal with both of these components separately here. So the expectation of AVFVFV is just like, so what does AV do to each component? So the part which is just proportional to the all ones vector, it leaves it as it is, right? So so this first part will be just this alpha v 1v, alpha v 1v. This will correspond to the part here that's just a constant times the all ones vector, and the parts that's perpendicular, well, I don't know, but soon we are going to say that this part is in fact very small. So because these local adjacency operators are lambda one-sided spectral expanders, then I can say that if I look at this, okay, it might be very large negative, but if it's positive, it's still less than lambda times the inner product of fv_perp, fv_perp. Okay, so I can say, and this is like, I think the only inequality that appears here in the proof, that this is less or equal to, I leave the first part as it is, plus lambda fv_perp, fv_perp. Okay, so so now I have like two parts that I need to calculate. What is this fv_perp, and what is this fv0? What is this alpha v, the scalar that appears here in inside of the inner product? So fv_perp will we will just write it as just fv minus fv0, okay, and then we can rewrite this as the expectation over 1 minus lambda, the first term, plus lambda fvfv. And if we look at the right-hand side, we know that fvfv in expectation is just supposed to be f inner product with f. This is again the use of the local claim. So again, this will be equal to 1 minus lambda, the expectation of the first part, plus lambda. So now we're left to understand, right, the problematic part, the part that prevents us to say that fv is perpendicular, the constant part. So in this special expectation inner product, the inner product of the constant 1 vector is always 1. Okay, so this, in fact, okay, this inner product is not very sophisticated. In fact, we have just alpha v squared everywhere. Okay, so we're looking at 1 minus lambda, the expectation of alpha v squared plus lambda. So if we will define a function g of v to be equal alpha v, then what we have here is, in fact, 1 minus lambda inner product of g with itself plus lambda. So for the last part of the theorem, we just need to understand who is this mysterious constant alpha v. So let's just understand what it is. So what should alpha v be? Because this all ones vector is part of an orthonormal basis, or in other words, it's normalized. If I want to understand who this constant is, I just need to project f to the space that's spanned by this vector. So in other words, this alpha v is just f of v inner product with this local all ones vector. And you can see that this is simply taking the average of over all vertices in the link of v of f of u. And now again, I look at this experiment. I'm sampling from the link of v some vertex and averaging out f of u. Who are the elements in the link of v? These are precisely, right, when does u participate in the link of v? Precisely when u is adjacent to v, right? Precisely when the edge uv is contained inside of x. And in fact, not only is this true, the sampling process is exactly identical to the process of sampling a u adjacent to v and taking f of u. So in other words, this is just, okay, this alpha v is just af at point v. So in other words, so when we plug this back here, right, we get that gamma is less or equal.
We don't see it.
Oh, sorry. I'll give you back here. So in other words, we get that gamma is less or equal to 1 minus lambda in AF inner product with itself plus lambda. So AF is just gamma times f. So we get that gamma is less or equal to 1 minus lambda gamma squared plus lambda. This is excellent. Why is this excellent? Because now I got an inequality that involves both gamma and lambda, and it's maybe a polynomial inequality, but the degree here is only 2, so I can actually solve this. I know the root formula, etc., etc. So I can actually solve this and get that either gamma is greater or equal than 1, or gamma is less or equal to lambda over 1 minus lambda. So now, right, it can be either of these. But now I'm going to use the assumption that the graph is connected, okay, to say that my gamma must be, okay, so gamma must be strictly less than 1, since in connected graphs, okay, in connected graphs, all eigenvalues except for the trivial one are strictly less than 1. Okay? So what we get is our bound. Okay, so that any non-trivial eigenvalues must be less or equal to this. So I don't know, this was maybe like in a lot of steps and many of them seem technical, but in fact, this proof has two main steps. The first one was this localization claim, where I say that I can compute AF inner product with itself by a convex combination of the local inner products. Okay, this is like a very nice observation, and it really exploits the specific structure and measure that we had on the simplicial complex. And the second step is to say, okay, on the perpendicular part, we know that A kills it, that it will be very, very small. So all we need to worry about is the part that's not perpendicular, the part that is the all one's function times the constant. And it turns out that this constant has a combinatorial meaning, and this combinatorial meaning is exactly, you know, somehow recursive to again this global adjacency operator. This is actually all there is to it. Good. So, are there any questions?
Suppose you apply this just for d equals 2. What is it saying?
What do you mean for d equals 2? For
Just like a normal.
For a normal graph?
I mean, if you say that each link is. I mean, it's also saying it's of course true for that too, but then I'm wondering what is so special about this convex combination.
So, in a normal graph, the d actually equals 1. Okay, the edges are like one-dimensional or something like that. So,
I see.
in a graph, the links of the vertices, they have no edges, right? They're like zero-dimensional. If you take a vertex v and you look at all its neighbors, okay, then the link will only be a bunch of isolated vertices. So there is no, there is no apparent way of getting something that looks like a localization. And it should be, and it shouldn't be, right? Because there are some deregular graphs that are great expanders and some deregular graphs that are not, but the links all look the same, right? They look like de-isolated vertices.
The d is 1 for the graph.
Yeah. Okay.
But can you say something about graphs? Like, you can look at the edges among the neighborhood of, let's say, instead of just looking at isolated vertices, if I know that the neighborhood of a vertex are expanding, in the sense that
so
edges among them.
what you're saying is like, let's ignore the whole simplicial complex part and just like look at all the, let's just look at all the guys that are adjacent to V, and let's like call the link of V like being all these and the subgraphs induced by them, right?
It's the same as taking the link of the click.
Yes, so exactly. Looking at this is just like saying, okay, let's take our graph and let's, wherever there is a triangle, let's just put the triangle as another layer. And again, you can ask yourself if the links would expand in this way, or what measure you should put on the triangle so it will expand. And you're not going to get anything new from this. I mean, either it does or it.
Graphs. Like, if I know that the neighborhoods are expanding, does it imply that the whole graph is expanding?
Yeah, so I think that if you know that the neighborhoods are expanding, then you can just apply this theorem when you think of x2 of the triangle set to just be all three vertices where all the edges are connected.
But then this measures that you get, the probability measures, do they get all messed up?
Yeah, so the point is that you need to carefully define how you're going to choose here a triangle, so that if you choose the edges uniformly at random, you'd get the same distribution on edges. So if the measure on the edges is uniform and you're deregular, I'm sure just actually I'm not so sure anymore, because a priori you could have like edges that don't participate in any triangle, and then you'd have to think about it. So maybe it's less general than what I thought. I need to think about it.
No, but then the link of that guy includes an isolated vertex.
Oh. Yes, that's true.
So you think there is such a theorem that you can?
Yeah, I think that you could probably maybe under some assumptions of regularity just reduce it back to this theorem, but I can't tell you like a definite yes on that. Good.
So there was an anecdote I can tell you. So someone came to me, he's trying to build like an e-democracy distributed network. Okay, so I don't want to get into the details, but the point is people kind of add themselves to your graph whenever they want, and they choose who to connect to. And he wants to maintain the fact that the whole graph is an expander. He said, all I need to do is whenever someone adds themselves, their neighborhood needs to look like an expander, and then the whole thing will... It sounds very nice, but of course, I have no idea how to construct such a thing, let alone distribute it.
So maybe just before I finish, I'll say that this guarded method technique, where you first look at some global operator, calculate it locally, and then say something about the constant part. Okay, something that can actually be reapplied in other settings in simplicial complexes. And
so how do you use this to actually give a new construction of expanders? Like, do you stitch together little expanders? How do you do it consistently so that all the links are expanders?
Yeah, so I don't know how to just construct expanders combinatorically, but so I can't use this theorem as is to just construct an expander because, as you say, it's not trivial. I don't know how to do it. If somebody already constructed something that they claim to be an expander, then I can maybe use this theorem to like analyze it much more efficiently. Because now, instead of like analyzing every link in this maybe very complicated simplicial complex, it's enough to look at links of a certain level, right, of the level of codimension 2. Right, and there, if I can somehow analyze them and say that they are very good expanding graphs, then I can use this theorem to say that the expansion trickles down all the way to the bottom.
So, like, suppose you take quotients of buildings where all the links are projective plane graphs. Does this imply that any quotient is an expander graph, the underlying skeleton?
Yes,
So,
as long
yeah,
as
if-
you don't quotient too much and doing the
link
the one ball around the vertex, it works.
Okay.
So is it natural to, as you go down several layers in the stronger version of the theorem, you have to lose on the expansion? I mean, if the expansion looks like 1 by d, you get nothing, right? If d is the order of the simulation complex, or d minus 1 is the order of...
Yeah, you're right. Like, if the expansion is, if the lambda here is half or above, then this becomes a trivial bound, right? If lambda is equal half, then this is just equal to 1, and then this is meaningless. And people know how to construct. People know how to construct expanders where this is half or above, and the graph is connected. So you can say something maybe more sophisticated on the bound to bound this to bound eigenvalues of the simplicial complex there. So this is by no means tight. Okay.
It's a sufficient condition.
Yes. You can find simplicial complexes where it's better.
Random regular graphs will probably have disconnected links. All their links will be disconnected. So, and they are very good spectral expanders. So.
Yeah, that's also.
This is an explanation of why it's far from being tight.
But I think that was the flip side of the question. I was wondering, could you, as you go D layers, could you hope for a better translation? Right? Like,
Oh, so you're asking if
if you go D layers, you said the composed bound gives you lambda over 1 minus d minus 1 lambda. Could you hope for a tighter, less loss in this expansion?
less loss
You go
than.
D layers. Right? It's not the same question.
Oh, I get it. So you're saying, let's like look at this proof, but instead of looking at links of vertices, let's look at links of edges and try to infer something directly to the... So the proof will work almost in the same way, and where will we get stuck? When we will try to calculate this alpha v, and apparently the constant that we will get here will not be anymore AF of v, okay, but it will be maybe another operator, right? It will be like if this is not a vertex anymore, if this will be an edge, this will be like an operator where I have like on one side all the edges participating, and on the other side I have all the vertices participating, and it will be an average operator of the bipartite graph where I connect an edge to a vertex if they all participate in a triangle. Okay, so this is, so in another work that me and Irit have, we actually do spectral analysis of this adjacency operator, and it's we call it the complement walk, because from an edge E, we pick a vertex V that complements it to a higher level set. But the problem is that in this proof, I don't get something that relates to gamma again. So naively, I don't know how to say something like that, but maybe, I mean.
Maybe it's in a perpendicular to your question, you're going to improve the t from d to 1 then. If I understand your question, instead of going d layers, you might erase the t layer and you might take 1. But note that in all the construction that, in all the places where we apply this theorem, the lambda could be very, very small. So you're improving a d to 1, but lambda could be, these are not just expanders, these are super expanders. So you're improving something which is insignificant for the specific cases that we know that.
So, did you say anything about how the trickling down thing implies the fact that the highest thing implies HDX? I mean, you wrote two theorems. Did you say anything about what the second one implies?
Could you?
I mean, so the theorem that if all the top level links are expanders, then the whole thing is in HDX. So that just follows from this in some.
Yes, it follows from follows from the first theorem, just because. I like to explain this maybe when I redraw the diagram that we saw before, right? So suppose I have a very high dimensional simplicial complex, and this is like the d minus 2 level, and I'm looking at and I have here the d minus 1 level. And when I look at a link of somebody in the d minus 2 level, it's like taking the simplicial complex that its diagram is everything that's drawn here above. So if I look at the d minus 3 level, right, so its link is actually, right, like everything that's drawn above. So if I know that all the links in the d minus 2 levels are very expanding, then when I look at somebody in the d minus 3 level, I know that all its vertex links, which are just these guys, are very well expanders. So I can infer that this is also a pretty good expander, right? So now I know that this guy's underlying graph is also expanding. So then if I look, yeah, so then if I look one level lower, then here I have more links and I can reapply the theorem. Okay.
I just wanted to say one comment on Sean's question. So we can, I know we thought on this, we can construct simplicial complexes where you have like d dimension for d large, but the top simplices, or like the co-dimension 2, have any small epsilon second eigenvalue that you want. That's a constant, independent of d. You can make it as small as you want, but it doesn't go down. So you would have roughly epsilon-ish eigenvalues all the way down the complex. So I don't know if that depends. So I'm saying Izar's thing says if you have 1 over d or 1 over 2d, you get all the way down, right? So the question is, what is the right thing? Like if it is like 1 over d, what happened? I don't know that. What I know is that you can get, give me any constant, I can build up a d-dimension for large d such that the top...
I'll give you epsilon.
You give me epsilon.
Then you take d to be much, much bigger than
Yeah.
1 over epsilon.
Yeah, but I give you a complex of 1 over of epsilon at the d minus at codimension 2, and everything down is also about epsilon.
All the way down. What does that mean?
I mean, it says a little bit of tightness of this. It doesn't say 1 over d. I don't know if 1 over d is the right bound, but it says that you cannot hope if the top complexes are like 1%, I mean second eigenvalue 0.01, that doesn't necessarily mean that you can go all the way down the state and get 1 over d.
Yeah, we know here too that 1/2 is tight. That follows from our constructions.
How tight in what way?
You couldn't, I mean, if you stated this theorem with 0.51, you'd be stating the wrong theorem. I hope that answers your question.
Okay, I understand what you mean. You mean that if I know a bound of 0.51, I should not expect any
It's a wrong statement. If you wrote this theorem with
expansion
0.51,
of the underlying.
yeah, because in our construction we can get as close to 1/2 as you, even if the global expansion is not very clear.
I think for half is a very
Yeah,
simple
for one,
example. Maybe you
for
can
1/2, just take the plane, tessellate it with equilateral triangles, and well, cut it and glue it as a torus, say, and then you can see that the jigger can be as bad as you like, right? But the links are still
Yeah, but that's a
hexagons,
single
so it's
example. Now we have
1/2
an
on the
infinite
nose.
family of examples that exhibit this.
Any more questions? Okay, so that's time to done. Time for the reception.